Okay, so as Marcus was saying, thanks a lot for having me here, well, virtually. We'll talk about the track implementation for the light dark matter experiment using a CTS. And thanks goes to Paul, which helped a lot during the process. Okay, let me see. Yes, so I'm gonna give an overview and motivation for light dark matter searches. This is because you probably never heard about this experiment. So I want to just give you an overview and explain why I'm doing that. We'll talk about having kinematics. Then I will talk about the LDMX, the light dark matter experiment detector layout. And then I'm going to talk today a little bit about conventional track reconstruction implementation using a CTS. So kind of a step back from all the newest algorithm back to, you know, basic Kalman filter and seed finding. I will then talk about what's our analogy strategy and where MIP tracking in calorimeter plays a role, and get some feedback about how to proceed there. So then I will give some summary and some next steps. So very, very lightweight. Okay, talking about thermal dark matter, just to justify our experiment. Thermal dark matter that originates as a relic of the hotter universe is one of the most compelling paradigms because it's generic. So you can have just a non-gravitational interaction between dark matter and standard model, and predictive because you need a minimum annihilation rate to actually justify the relic density in the universe nowadays. So a lot of time was spent looking for WIMPs. We didn't find anything so far. So focus is now shifting toward light dark matter. And light dark matter, in order to have the relic density, you need a new mediator. So some sort of something that connects the standard model to the hidden sector. This can be, for example, a dark photon. If you assume that you can have a U1 symmetry extra to your Lagrangian, which mixes with the electromagnetic photon. So in this way, you can have basically a portal between the hidden sector and the standard model, and then you can have annihilation, scattering, etc., etc. Okay, so what are the possible signatures in this model? You can have, if we think about direct annihilation, so basically dark matter that annihilate into a dark photon, and then this is the case into standard model particles. This is possible if, for example, the A prime mass is smaller than the mass of the dark matter. If instead the mass of the A prime is bigger than the mass of the dark matter candidate, then it will decay into dark matter particles. So we're going to focus on that today, and this leads basically to production of dark matter, which escapes detection. And we're going to observe basically missing mass, energy, or momentum in our detector. It's important to look for that because since working on the paradigm of thermal origin of dark matter, this means that there must exist an interaction between light dark matter and standard model. And so it must be possible to reproduce it in some way in accelerator-based experiments. If you think about the diagram I showed you before, if you just rotate that, then it's possible from standard model particle to produce dark matter. And one of the most sensitive ways to search for this production is using an primary electron beam on target in order to produce dark matter on fixed target collisions, as it's enlightened in the slide. Okay, so just a very few on sensitivity. We do have several experiments looking at this type of physics. One is, for example, an A64, which is a little bit shy from the exclusion or the probing, actually, the candidates of this model that will give the right relic density in the universe. So we have a clear prediction as a function of the mass of the dark matter and the target of particle type. So after boring you with this introduction, let's talk about LDMX experiment and the missing momentum search that we do and why tracking is important for us. So the kinematics of our experiment actually are very simple. You have an electron beam that arrives on a target, and then you assume to have dark stratum in the target, and you emit an A prime at a very shallow angle that depends 1 over the energy of the beam to the 3/2 power. And then this A prime decays into dark matter particles. From the target, you will have a recoil electron emitted at a certain angle that depends on the mass of the A prime of the dark photon. And so it's very important to measure this recoil electron precisely because this is linked to your signal. It's linked to the mass of your signal. The main background to this physics is clearly Bremsstrahlung. On the right part of the slide, you can see that you have an increasing single electron background in black that peaks at 4 GeV. 4 GeV is the beam energy that we use for this experiment. And then you have the Bremsstrahlung tail. And oppositely, you have the dark stratum that will actually have the energy of the electron, of the recoil electron, that is going to be very soft. You can measure the energy with a calorimeter, but you can also measure the momentum of the recoil electron. And you can see on the bottom part of the slide, as I was saying before, it's very discriminant in finding the mass of the A prime. So it can be used for signal identification rather than background rejection. Okay, so what type of experiment we designed? So we designed an experiment that has basically a tracker that measures the incoming electron. Then we have a trigger scintillator that is used to count how many electrons we have in the bunch. And then we have a recoil tracker. And then in the recoil tracker, we measure the recoil electron. Then we have a calorimeter that is going to look for basically nothing else than an electron. So if you have Bremsstrahlung, you basically will have a photon that will be emitted from the target, and it's going to hit the calorimeter, the electromagnetic calorimeter, and leave a signal, and this is going to be rejected by our detector. So our detector basically works as a veto. We want to veto everything that doesn't have just an electron in the recoil system. So this experiment is going to be built as LAC. We will use parasitically the CLS2 transfer line, basically the LISA, the LINAC end station A. And we plan to use in our phase 1 a 4 GeV beam energy where we have a single electron per bunch. This is a very simple scenario with respect to what we're talking all the day today, which we are talking basically to LXC and very high pileup. Here we have just a single electron incoming, and we want to measure extremely precisely the momentum of the incoming particle and the recoil electron very precisely as well. What are the backgrounds that actually have an impact on this analysis? So at a very basically at the highest rate, you have just an incoming electron and an outgoing electron, very easily removed by tracking. And then it's going to have Bremsstrahlung, and then the gamma in the calorimeter is going to go through a various set of different processes that are going to be rarest and rarest and rarest till. And then we have basically whatever is visible is going to reach 16 order of magnitude. So we have to be very careful with the combined tracker and calorimeter to remove everything to the 10 to the 16 in order to be basically at the same level of the invisible background where neutrino are produced. There are different veto handles that can do that. One is, of course, tracking, and the other one is going to be related to the calorimeter. It's going to talk a little bit later about that. So the LDMX detector concept, it has, as I say, a tagger and a recoil tracker, and then it's going to have at the end electromagnetic and hadronic calorimeter for detection. The electromagnetic calorimeter, it's basically a silicon wolframium sampling calorimeter, 32 silicon layers. It's similar to it's basically based on the high-regularity CMS calorimeter, and it provides transverse and longitudinal shower shapes. Additionally, we can do tracking using isolated charge for removing isolated charge hadrons, and it's used also for missing energy trigger that basically basically, as you can see on the bottom part of the slide, we require everything that has a deposit in the calorimeter lower than 1.5 GeV. The hadronic calorimeter has been optimized to stop neutrons at 2 GeV, which are the hardest particle to basically stop and observe. And it's based on the mu2e cosmic ray veto, and it has the sampling calorimeter as well, and it has alternating X and Y orientation of the scintillators in order to provide, let's say, some sort of 3D points that we do some MIP tracking for calibration. Just to say, this has been designed and commissioned here at CERN during October and April test beams. Okay, let's move to the trackers. So the trackers, we have two trackers. The first one is actually included in a magnet bore. So where the magnetic field, of course, to measure the momentum, it's fairly constant. As you can see on the bottom part of the slide, it is a projection of the field strength as a function of Z along the beam axis. And then the various lines show you moving along X, what is the field strength. However, the target is actually placed at the end of this magnetic field, where the recoil is immersed in the fringe field, a very steeply varying magnetic field. This is this is actually intended because what you have is that you have incoming electrons at 4 GeV, and then you have recoil electrons at around 50 down to 50 MeVs that you want to be able to measure. So we talk here about a few orders of magnitude of difference, and then if you want to maintain an electron that actually leaves enough hits in your recoil tracker, you need to actually curve it not too much in order to make it travel through all your various layers and have actually hits in order to reconstruct properly your track. So this is actually an intended scenario. However, it complicates a bit the track reconstruction, of course. So as I said, we use ACTS right to start up from the bottom up. This experiment has been thought around 2015, had no tracking, and basically we started working on implementing everything from the basic at the end of 2021. So this is actually a fairly new framework at the moment, so don't be too judgmental on that. So we use a CTS, as I said, which after evaluating several libraries, we thought this is the best, the natural choice to go with. And we used one of the latest version, 18.00, just to give some details. This is used in different, the CTS already has few applications. One is Atlas ITK, and then it's extended to Pandas, Phoenix, and Bell 2, as well as Phaser, which is basically a competitor. So the LDMX tracking workflow is very similar by conception to let's say Atlas way of thinking. So we have space point formation, seed finding, then we have track candidate formation using a combinatorial Kalman filter. We run an ambiguity solver, well, not really, because we have a single track at the moment, and then we try to match tagger and recoil tracklets in order to have a full track, or in the case, estimate, for example, the direction of the photon emitted in the target by checking the angles between the target and the recoil tracklets. The first step in order to start any track reconstruction is actually to have a handle on the geometry coded inside your reconstruction framework. So I've basically parsed the D4HAP based geometry that we use for LDMX into the ACTS so-called tracking geometry. This has been, let's say, the most time-consuming job, because there were some tricks to be done in order to convert some things for telescope geometry as I wanted. But as you can see from the plots here, this is actually implemented, and the full tracker has been actually loaded inside a CTS and can be used for track reconstruction, layout studies, and so forth and so on. The first step is to run seed finding. I used the seeding algorithm from ACTS, which I adapted to the telescope geometry just with basis configuration. The 3D space points are grouped in phi and z, and I've tuned the configuration to allow for the LDMX beam spot, which is quite large with respect to what we are used to think about in Atlas, for example. It's a 40 by 40 millimeters and 10 by 10. So it's basically the whole target is going to be illuminated by this beam. The tricky thing is to actually use this type of seed finder inside the recoil, because the seed finding uses the hypothesis that the track is actually following in an helix trajectory. But the idea behind the layout of the recoil is such that it's approximate quite good an helix if we assume half of the magnetic field that we have in the Bohr system. So to run the actual seeder, we use 1.5 Tesla in the target and the half 0.75 in the recoil. On the bottom part of the slide, you can see the zero and momentum reconstructed in the target. Just had these plots. And you can see that this represents the size of the beam spot and the 4 GeV momentum of the beam electrons. The next step is to actually basically check the propagation along the magnetic field interpolated map. And this is used by still via ACTS routines that uses an adaptive Runge-Kutta step, which is basically showing on the bottom part of the slide the propagation of an incoming electron through the Tagger volume, the target, and the recoil volume. In this case, just for display, the interaction with the target is neglected in this plot. That's why you see a very straight and smooth line. You can see at the end of the recoil volume that the track starts to basically straighten up, and then it exits the magnetic field and it goes straight to the calorimeter. Track finding is based on the combinatorial Kalman filter provided by ACTS, fully ported inside the LDMX SW, which is our software reconstruction. It uses dedicated measurement selectors to accept or reject measurements. And currently, we only use basically, as it's pretty fresh work, so we basically use the best heat that it's associated to the track hypothesis. So basically, we have a single track per every seed that we have. We don't have still a digitization. So in order to do all these studies, we take the GEM4 3D space points, we project them on the relative sensor surfaces, and we take the only 1D strip measurement that is mirrored by the expected resolution, which is about 6 microns. These, let's call it event displays, shows the effect. So basically, it shows the first track that has been found for the LDMX using the ACTS suite. And I decided to show basically a track that undergoes a very energetic BREM in the third layer, which shows basically the propagation performance in the fringe field. You can see that there is a large kink at the beginning, and then it straightens up, and then you see that it properly actually fit through the various hits. For the first phase, where we're going to have a single electron per bunch, a preliminary track finding efficiency, which is defined as the number of tracks that have leaves at least 8 hits over the number of truth electrons, is expected to be above 99.93% for the Tagger and the recoil tracker. And this has been checked on brainstorming samples only. So pretty okay for a first try. This plot shows the momentum reconstruction in the Tagger and the recoil. On the top part, you can see the momentum reconstruction for the Tagger electrons. You can notice that I've used different smearings between 5 to from perfect to 10 micron in order to study what is because from that depends what type of chip we're going to use to read back the silicon. You can see that basically for the Tiger, we're going to have about 50 MeVs of resolution over 4 GeV, which is about a little bit more than 1%. For the recoil,
you've got 5.
Sorry?
You've got 5.
Okay, yeah. So for the recoil electron, you can see that on black you have the perfect, the truth electrons, and you can notice that the Bremsstrahlung tail is fairly well modeled by this preliminary approach. Truth residuals, we compare the track parameters with respect to the truth, and you can notice that those are fairly Gaussian, centered on 0, so no bias, and the resolution are difficult to see, but basically you can see that they look pretty good, as well as the recoil truth residuals for the track parameters. We are still studying about the momentum, that's why it's not shown here today, but you can see from the other parameters that the residuals look fairly good and healthy. The final thing about the tracking workflow is Tiger and recoil matching. You can notice basically the Brem photon direction is important input to the ELBDT, and I'm going to talk a little bit later very fast. And this is basically in order to match the target to recoil, we're going to use basically a distance in the impact parameters. And in the bottom part of the slide, you can see let's say the resolution on the bottom right part of the slide, the resolution of the delta, the 0 between target and recoil, as a function of the recoil electron momentum, which is flattens when the momentum is high, and then it goes up to 200 micron of resolution for low momenta. So very briefly on the analysis strategy, I said that there are several processes that need to be removed. Most of the job is done from the tracker to remove charged particles. Whatever happens in the calorimeter is removed in the electronic calorimeter by a BDT, which is basically dedicated to remove everything which is depositing energy in the electronic calorimeter. And then whatever it punches through and leaves hits in the hadronic calorimeter is removed by just basically counting the number of hits that are left in the hadronic calorimeter. Whatever is not removed by this, it's actually considered to be basically a kaon that decays in the ECAL. And this is actually identified by MIP tracking in the high granularity calorimeter. There is a drawback that basically the algorithm that is present now uses basically plain linear assumption for these charged hadrons, and they have to be close to the photon projected direction. Kink tracks on the bottom part of the slide, you can notice in a kink between this kaon and this muon, they are not reconstructed. So this is something that will benefit of discussion, of course, from experts present here on how to try to approach that. So just to conclude, the sensitivity is pretty good for this experiment. After we will have a background-free search for GeV electrons. We expect to have basically coverage, basically up to 100 MeVs, where we can basically check or rule out this type of model at different hypotheses of this dark matter candidate. So to summarize, basically, LDMX is an electron beam on target experiment that's designed to probe sub-GeV mass range for thermal relic dark matter. We focus on invisible signature. Nonetheless, we need to reconstruct what we see in order to remove those events. Track reconstruction is a fundamental step in LDMX event reconstruction, and we use for conventional track finding and fitting the ACTS library with minor modification or configuration for telescope geometry. There is some work to do, of course. This is just the beginning, but there are exciting times ahead since the experiment is moving from concept design to actual creation.
Yeah. Thank you. When I saw the number of slides, I said, whoa, but you made it. Really
Thank you.
I don't see any hands raised on Zoom. Is there anything in no other question in the room? Andy.
I put it into this new system, yeah.
Did you know?
Yeah, it is. It's not popping up. I don't know. Yeah, Francesco, thank you. I'm not going to ask an ACTS related question. That's stupid. But I'm going to ask you a question for the calorimeter. Are you guys considering using the clue package for the calorimeter reconstruction? That's designed for exactly this type of calorimeter, and now has been also open sourced and decoupled from CMSSW, as I understood from Erica.
So as I write in the slide, the initial algorithm has been developed by UC Santa Barbara. So I have no idea if they actually plan to use this package you suggest, but I think it's a good idea to keep an eye on that. And I can follow up with. I am not aware of any decision to use it. Actually, they just bumped me this problem of king tracks, so probably it's going to end up on my basket. So actually, we'll follow up with you on this, because yes, I know that CMS has the same hardware, so they must have some sort of library or package that can.
No, they have. It's called Clue, and I would find that an extremely nice and strong statement to use two open source algorithmic packages from coming out from Atlas initially and CMS and combine them together.
Yeah, that would be cool.
That would be an extremely nice community project.
Okay, I'll follow up with you so you can give me some pointers and I can try.
Yeah, I was actually about to ask the same question.
Okay.
So my question is gone as well. Are there any other questions?
Yeah.
Oh yeah.
Hi, this is Salva. A question on your page 28 on the reconstruction of the scattering electrons. So on the upper plot, the tail is due to what? Is it to the? I mean, is it being simulated or is it being? Of course, it's been simulated, but I mean, is this the Strandung trail or this is just an issue with the reconstruction?
The top plot. Yeah, you have material effects in the tracker. The tracker has a certain X0, and of course you can have energy loss due to Brem in the tracker itself.
So there is no way to recover any Bremsstrahlung before the layer and so on.
Well, it's gonna. So this is. I don't know in this case if we could use some. If you could actually use the a GSF to better estimate the momentum. But you will have material effects because you do have material. The tracker has material, so you will have this tail. But probably I'm not an expert in using GSF myself. I have never actually worked with the fit, but it's something I actually would like to investigate for this case.
Maybe this is my question. Is has no sense.
We have a GSF fit prototype available that should be able as a refit. That was my second comment. I put into the system.
into the non-working system.
It's like a bug tracker. You give it there to make it disappear forever.
Okay. All right.
I cannot hear. I can't hear you very well.
I think I typed it, yeah.
I think this. Andy was just commenting on the existence of the tool and what you can do.
Yeah.
There's a question over there.
Yeah, I was going to make the same comment.
Okay. So
I typed it in the wrong because there's a few
it changes and you did it to the previous.
I apologize. Yeah, it's for
Yeah.
track finding new recognition wrong.
Okay.
I deleted.
So your question was, or your comment was already done, yeah?
Yes, and
Okay.
you said the same thing I was going to say.
I see no other questions or comments, so thanks, Francesco, again.
Thank you very much.